Hello, everyone. Thanks for joining on Zoom. Um, all right, let's get going. We've been talking about feature selection, and at a high level, the main idea is that if we use too many features, we know that our error variance is larger than we want. On the other hand, if we use too few features, we get penalized by a large bias, meaning our model is not as sophisticated as the model generating the true data. And so really we want something that is doing a good trade-off between those two different quantities. Um, and one way to do that is to use only the subset of features that are most important for your prediction task. So that is our goal. We have always D total features. We want to find whether we can remove some of them and exactly which ones. And we said that what's challenging about this is that the total number of possible subsets we can use would be 2 to the power D. And that number grows very quickly in D. So once you have D more than, depending on your resources, maybe D more than 20 or so, you just really can't handle those problems. Or you can't consider all the possible subsets. But anyway, if for some reason you could consider all the 2 to the power D possible subsets, then the optimal strategy is you use each one at a time, you train a model, you test it on some test data. For example, you could use k-fold cross-validation to do that, and you're going to get some sort of performance score for all 2D subsets, and then you simply choose the subset that gives you the best score. That is the optimal approach. But as we said before, in many cases, we cannot do that. And so we're forced to use some sort of suboptimal approach. Last time we talked about stepwise selection or regression, where you first find the first, let's say, we talked about forward selection. You use the single best feature, figure that out using cross-validation. Then you keep that feature and you use is something okay. I was just seeing there's some messages. Does is does it change if I change the size of this or not? Okay, I'm not really getting any feedback, so let's continue. Um, okay, so with forward selection, you select the single best feature, and then you look through all the remaining features. You add the next best one according to your cross-validation score, and you keep doing this. As you add more features, your bias goes down, your variance goes up. But in doing this, you can find the best trade-off between bias and variance, best number of actually best subset of features. You can also do a version of this where you start with all features and you remove them one at a time. That works pretty well, although it's not optimal. Another approach which I think doesn't work as well in practice is doing something like looking at each feature to find which one is most strongly correlated with the target. That allows you to rank your features from most correlated to least correlated. And then you could, if you have this ranking, now it's just a matter of how many of the strongest correlation features do you use. You've turned the feature selection problem into a modeler selection problem, which is computationally tractable because there's many fewer things to consider. And if you didn't like correlation, there's other statistics you could use. In all cases, these are univariate statistics, meaning you're only looking at the relationship between a single feature and the target at a time. And that's one of the reasons this is suboptimal. Okay, so what we're going to talk about next is regularization, which we'll spend much more time on. So this is the idea, is that until now, what we said we want to do with linear regression is that we want to choose the beta vector that is the minimizer of the RSS as a function of beta. And what we know is that the RSS as a function of the beta vector is the sum over our n training samples of the true targets minus the predicted target y hat I, which is going to be some function of beta. Okay, so that is what we want to do. But we know that one of the issues here is that one of the issues here is that we are at the moment just assuming that we're going to use all of the features we have available. And the question is like, how do we handle this if we want to use fewer than all of our features? So one of the things to realize in linear regression or any sort of linear prediction method is that if you set one of the coefficients to 0, what that means is you're just going to multiply that feature by 0, which means you're not going to use that feature for prediction. So basically, doing feature selection is the same thing as figuring out which subset of your beta coefficients are going to be set at 0. And so the idea is, at a high level, we don't want to use feature. Why don't use for any given feature j? We don't want to use it unless it's really helpful to reduce our RSS. And so one of the ways we can do that is instead of just minimizing RSS like this, we add one more term to what we optimize. So here we're going to do arg min over the beta vector of, we're going to call capital J, it's a function of beta. Well, now J is our optimization cost function. That's going to be the RSS as before. But now we're going to have one extra term we'll call phi of beta. And this thing is called the regularization term. So for the current purpose, since we want to turn certain coefficients off by setting beta hat to 0, this regularization term should reward us when the betas are 0. So that's the idea. So this sort of goes like this. So if you didn't have the regularization term, the beta that gives you the minimizing beta, is the one that minimizes RSS, which, as we know, is the least square solution. But that can overfit to these coefficients or these features that are not really useful. So we add this other term, and this other term says, I really want all the features to be 0. And so these two terms now are used together. And this first term really doesn't want the features to be 0. If you set all the features to 0, your RSS is going to be terrible. It's going to be high. On the other hand, if you set all your features to the least square solution to minimize RSS, this other term is going to be unhappy because it basically doesn't like large values of beta. Somehow it wants to make the betas 0. So these two costs, or cost and regularization, when used together, you're going to find some sort of balance between the least square solution and simply setting all your coefficients to 0. And so for us, the main question is, how do we design this cost in a good way to do what we want to do, which is feature selection? All right. Any questions so far? Okay, so let's see some details. So we're going to be covering 2 types of regularization, which are the most commonly considered regularizations. So we have, first of all, L2 regularization, which is going to be some scalar constant alpha times the sum over my different feature indices of the squared. Let me just actually focus. Beta j squared. And if you look at this, you can see that this is essentially the same thing as the norm squared of the beta vector. And it's the 2 norm, the Euclidean norm. So that is why this is called L2 regularization. On the other hand, another option for us is to use alpha times the sum of the absolute values of the beta coefficients. And you might remember that this term without the alpha is actually the L1 norm, or the L1 norm, and this is why it's called L1 regularization. And so when we plot a single version of these two, you can get a sense for how they differ. If you look closely, this L2 regularization, it curves up more sharply here. As beta starts getting bigger, it complains more than L1 regularization. I guess another way you could see that is you sort of cut a line down here. So for this value of beta, you can see the cost for L1 regularization is lower than the cost for L2. L2 is kind of complaining more loudly about that value of beta. On the other hand, when you look at the betas closer to zero, you see it's the opposite. You see that actually L2, or beta squared, doesn't really care as much if you have betas different than zero but close to zero, whereas L1 is only happy when the beta is exactly zero. As soon as you start deviating, it starts to complain loudly. So this will give us a sense for how these two different regularizations work. So as we'll see, the L1 regularization is much better at keeping your coefficients really at zero, a subset of them, whereas L2 is not as good, but as we'll see, it has other advantages. There's other reasons we might want to use it. Okay, so both penalize deviations in beta j from the value zero, but just in different ways. Let's see. Okay, so another thing you can note is that there is this scaling alpha, which just controls the overall strength of the regularization. Alpha is just going to be some non-negative number, and this is going to be something we have to choose carefully because it's really going to affect the trade-off here. So as alpha gets larger, essentially means you put much more emphasis on keeping the coefficients close to zero. And if alpha is small, it means you really care mostly about minimizing RSS. You don't care as much about keeping your coefficients close to zero. And one other thing to notice is that our index j, we start counting at 1, meaning we are not involving the intercept term beta 0 in our regularization. This is traditional. You could add it, but it's not how it's usually done. And so basically we let the intercept term just be whatever it is without any penalty, but it's the other ones that are controlling our features. Those are the ones that we want here to, essentially we want that a subset of them is exactly equal to 0, at which point we will be ignoring those features. Okay. Any questions on what we have here? Okay. All right. So now there's sort of one important issue we have to tackle when we kind of look back at these equations. We can notice that all the different terms j are being treated exactly the same. And that only makes sense if all the different betas are alike. And what I mean by that is that if you think about a linear regression model where you have y hat is beta 0 plus the sum for j times beta j xj, you can see that the overall contribution of a feature has to do with both the size of beta and the size of x. And when you download a data set, you never really know, what the sizes of x are. It could just so be that maybe some of these x's are absolutely tiny, for some j, whereas maybe for some other j, these are massive. And so if I have some really tiny xj, the only way to make those affect my prediction is to make those beta j's large. On the other hand, if I have some massive xj, the only way to keep those from dominating my prediction is to make those beta j's small. And so if my data is scaled in such a way that some of my beta j's are massive and some are tiny, this regularization is not really going to work correctly because the way that I'm penalizing the coefficients sort of, assumes that they're all around the same size. So in order to fix this, we're going to have to normalize our feature data. And this is something we can just do. We download the data, and this might be the very first step of pre-processing it. So the most common way to normalize your data is to make the, this is for the jth term. We're looking at the average squared term for feature j. And we're taking the average over our training data set. So we want to make sure that this is the same for all j. And so the easiest way to do that is just set that equal to 1 for all j. That's the typical way you normalize the scales of the x's. And as we also know, we've seen this, this equation before, back in Unit 2. When you take the average of the square of a series, that's the same thing as the squared sample mean plus the sample variance. So, you can see how both of these terms contribute to the overall, you could say, energy of that feature. So we'd like to normalize that. But there's one other thing we can do, and is often done, which is we learned this also back in Unit 2. If the sample mean of the targets, as well as all the features, are 0, so here we're taking the mean across the I index, then we saw that the intercept term vanishes, it goes to 0. So this sort of is a shortcut. If we normalize our data this way, we don't even have to compute the intercept coefficient because we know it's 0. And conveniently, some of our equations will simplify and so on because we just know that term is 0, we don't have to include it. So this is another kind of standard thing to do. It's not essential, maybe in the sense that this is, but it's often done together. Both of these things are done together. So removing the sample mean. Okay, so putting those two things together, this is what's typically done. And when you combine them, these two things together, you call this standardization. So what you do is for every feature, you take the raw feature, you subtract, if this is the jth feature, you subtract x bar j, which is the sample average. And then you divide that by the sample standard deviation for that feature. So shifting and scaling. And when you do this, you get this thing here satisfied simultaneously. You get the sample mean to 0. So you do this for every one of your samples in your training data set. You do this. Basically just say you take this original sample, subtract the mean, scale it, and that becomes your new standardized sample. We do something very similar for the targets. Yi minus y bar over sy. Now this one is definitely not, it's not needed for regularization. The only reason you might want to do this is to make your intercept coefficient 0. But for a lot of the notes, we'll just assume that that is what's done. Okay. Any questions on the standardization? Okay, so standard way to do this is using sklearn. They have some different, in the pre-processing library, they have different scaling methods. They call them scalars. This is the standard scalar. And so what you do is this X0 matrix in the demo contains all our training features. And when you do fit transform, it does two things. The fit part of this computes the means and the standard deviation. And then the transform part actually does the shifting and scaling. And notice for Y, we're again doing fit and transform. But one thing that is just sort of a minor detail. This function assumes that this is a matrix, that it is a 2D array. But our Y thing is actually a 1D array. And so we need to just temporarily reshape it to a 2D array, which is basically going to be like a matrix with, I think in this case, a single column. So, it's just a different way of looking at the same array. But once it's in that form as a 2D array, now you can apply fit transform. Now, if you didn't move it back, some other functions in scikit-learn would explain. So here, this reshaping is basically saying, let's convert that back to a 1D array. So that's vector to matrix and back. Okay, but once you do this, now we have our standardized training features and targets. Okay, so and now that we have these, we just go ahead and we do the usual thing of designing the predictor. Now, we have to think about what are we going to do with the test data, because this is all the training data. So the mistake that a lot of students make is they just do exactly the same things to the test data, meaning they take the test data, they plug this in here, fit transform, and test labels fit transform. So the problem when you do that is that because the test data has different means and variances, the standardization that you apply on test and training would be different. And as a result, when you train, according to this training data and you apply it to test data, there's going to be a mismatch. It's never seen data scaled that way before. So basically shifted and scaled that way. So you want to do exactly the same thing you do. Whatever you do to the training data, you want to do that same stuff to the test data. And that means that for the test data, you shift it by the training mean and you scale it by the training standard deviation. Okay, so that's what I mean down here when I say standardize the test data using the training statistics, not the test statistics. The statistics being all the xj's for j equals 1 through d and all the sxj's for j equals 1 through d. And same things with the y's. Y bar, s, y. Okay. And if you make this mistake, what happens is, maybe the results are okay, but they're just not great. And so when you do this in the final project, your performance is just a bit worse than everyone else's, and you do worse than the kind of competition, and you get a worse grade. So it's something that even though I say this every semester, there's always a number of students that still make this mistake. So I'm saying it again now. Try to remember it for later. All right, so that's standardization. Any questions on anything on this page?
When we standardize the training data, do we need to apply some sort of formula to the beta variables afterwards to make it fit the original data or no?
It's a great question. So the simplest thing to do is whatever data preprocessing that you're doing here, shifting and scaling, you do that always. So, whenever you get a new test sample, you don't use it in its raw form. You shift it and you scale it by exactly these quantities. So that's what I would say is the simplest approach. Now, with linear regression, it is actually possible, if you do this stuff, it is possible to figure out a new set of beta coefficients that would work on the raw features without the shifting and scaling. It's possible to do that. There may even be a homework problem on it, but it's kind of overly complicated. I would say, like, once you compute these quantities, and you actually do that in scikit-learn using the scalar.fit alone, then you can just apply that to your test data. And I think that's the simplest thing. Then you don't need to mess with the beta coefficients because they're going to be the same. You train them, and then those same coefficients will work on your test data.
Gotcha. Thank you.
Sure. All right. Any other questions? Okay, great. So, all right. So now that we have that down, we can kind of return to our ideas here, where we said we're going to take RSS, and we're going to add to it one of these two regularizations. Okay, and so here we're doing exactly that. So here's our RSS, spelled out a little bit more in terms of the true targets and it looks like, I think there should be subscript I on these y hats. Okay, so this is the true training target, and this is the prediction of the corresponding true training, prediction of that corresponding training target. And so here we have our L2 regularization. And when we use L2 together with RSS, There's a specific name for it called ridge. I don't really know the history behind why it's called ridge, but that's what it's called. On the other hand, if instead you use L1 regularization with RSS, that is called lasso. And lasso stands for least absolute scaling and shrinkage operator, but everyone just calls it lasso. So ridge and lasso are RSS plus either L2 or L1. And we can also write these expressions, these cost functions, in terms of norms. So here I have the RSS. We've seen this before. You can write it as y minus capital X times capital beta. And the L2 we can write as alpha times the beta vector Euclidean norm squared. So here I just want to point out a couple things. So I could write a little 2 in the subscript down here. But I'm not going to do that for the moment because I want to emphasize to you that when you're dealing with vectors and when you see a norm without any specific information about what norm that is, you always assume that it's the Euclidean norm. That is a standard norm for finite dimensional vectors. So since it's a standard norm, I'm not even going to write the 2 there. On the other hand, I can write this for the L1 norm. Again, with the norm quantity, but now I need to put the 1 in the subscript because that is not the standard norm. That's something special. Okay, so that's one thing I want to mention. The other thing I want to mention is, I don't know, was anyone surprised that this is not the A matrix here? We're used to seeing like y minus a times beta when we write RSS. So why am I using the X matrix instead of A matrix? Okay, so we're using the X matrix. If you remember, the A matrix was a column of ones next to the X matrix. But the thing is, remember our beta vector, because we've done the standardization, we know that the first coefficient in our beta vector is going to be 0. So that means that when it multiplies this matrix, it's just going to multiply this times 0. That's going to vanish. And so really, we don't even need to talk about that. Here, we're defining beta vector, not even including any intercept term anymore. It starts at beta 1, not beta 0. And therefore, we just have the X alone in these equations. So, yeah, any questions on this page? Okay, so let's kind of see, let's see what happens with, we'll start with ridge regression. So first of all, okay, I'll write down the cost again in norm form. This is y minus x beta squared plus alpha times norm of beta squared. So this looks a lot like RSS in Spirit. We have a squared norm here, a squared norm here. This is a differentiable cost. It's actually relatively simple. It's quadratic in beta. We can use exactly the same derivation procedure to minimize this that we did before. You take partial derivatives of this ridge with respect to each of the coefficients. You set that vector to 0, and you solve for the beta that makes that happen. There may be a homework problem on this. It's just, again, like I said, using exactly the same methods from before. But here's the answer. Here's what happens. You get X transpose X, that matrix, plus alpha times the identity matrix. That thing gets inverted. And then you have X transpose Y. And one way to see that this is consistent with least squares is that if I set alpha to 0, this goes away. And then I just have standard least squares. And here the same thing would happen here. And now that's the formula that we've seen before. So when you add this term, what it does is it adds this scaled identity matrix to the thing you're inverting. And so one of the things we notice here is that even if this matrix is not invertible for some reason, one of the reasons we saw is if you have fewer training samples than you do features, we know that this is non-singular. You cannot invert that. But for any positive alpha, once you add that identity, this matrix is invertible and you can always invert it. So this is one of the ways to handle invertibility issues with this is L2 regularization. Okay, so anyway, this is the beta vector. It can be derived in closed form. It can be computed this way. So let's see what happens. This coefficient path plot, which is right here, is super informative. So what we're showing here is we're showing, as a function of the regularization strength alpha, we're showing how the coefficients evolve. So in this demo, I think there's 8 coefficients. And notice what happens when alpha is 0, this goes away and you're doing least squares. When alpha is really tiny, this term is negligible. You're essentially still doing least squares, with some very minor changes. And so that's what happens here. When alpha is small enough, the values of those coefficients, there's 8 of them here, those values are basically going to be our least squares values. Now, as alpha gets bigger and bigger and bigger, eventually we have a situation where when alpha is so big that this term dominates this term, we can essentially just kind of ignore this term and say, for large alpha, you're going to be minimizing this. And the value of beta, the value of the beta vector that minimizes this is 0 vector. So that's what happens for very large alpha. Take very large alpha, and this vector of coefficients converges to 0. So what's interesting are the values of alpha in between. Here you can see what happens. You can see the coefficients, they start to shrink. They start to get closer and closer to 0. But interesting things happen along the way, like this brown one starts out negative, but it eventually changes sign. And it gets kind of big again before it gets small. So different things happen here. But what does not happen is this beta vector, none of the coefficients go to 0 until alpha goes to infinity. There's really no, I mean, okay, once in a while you'll have, like, for an instant, this coefficient went to 0 and this one and so on. But basically, you're not finding alpha for which the betas go to 0, and you're not doing feature selection. Okay. Larger alpha gives smaller magnitude betas, but not 0 betas. So even though we talked about wanting to do feature selection with the regularization, this regularization is not doing it for us. Any questions on that? Okay, so now you might wonder, okay, why are we talking about this then? Well, it turns out that this ridge regression is a very important function, and it's sort of used when it's used for a different reason. It's used when the features are highly correlated, meaning like if feature 1 is very similar to feature 2, there's issues that can happen if you don't control that. And essentially what happens is we can take a look at the least square solution. This is just doing least squares, no ridge regularization. So when the feature is very correlated, what happens is some of the components of this inverse matrix get very large. And those large components here create large values of least squares beta. And if you have a beta vector with some large numbers in it, that means that once you're done training and you apply this to a test sample X, those large coefficients in your beta vector are going to be very sensitive to small changes in X. And so small changes in X will affect Y. And essentially, this is going to be kind of an overfitting problem. We get very sensitive to like noise. Noise gets amplified through these large beta coefficients. That's a bad thing. We'd like to avoid that. So here we have another instance of bias variance trade-off. So we know that there's sort of an issue as alpha gets larger, our coefficients get forced to 0. That's also not ideal. But maybe there's sort of, there's a problem. Our variance is going to be too large here. Our bias is too large here. But somewhere in the middle is where you find the best trade-off between bias and variance. And finding that alpha is actually relatively easy. You just use cross-validation. You make a grid of different alpha. You do our standard, k-fold or whatever cross-validation procedure you want to do on those different alphas, and you find the one that minimizes RSS or MLC or or whatever, whatever you're interested in minimizing. Okay, so that's sort of how you do it. Let's look at a quick experiment. So what I did, sort of a toy experiment, but it proves the point. So I made an experiment where I made some synthetic data that it had two features only. And it was the true model was just a linear model, and I added some noise to the to the targets. But importantly, there's a lot of correlation. The features that I generated were very strongly correlated with each other. And so what happens is when you look at the least squares values of the coefficients, okay, so first of all, the true values of the beta coefficients were 1 and -1. Those are the true betas. But when I did least squares, I was getting these very large values like -30, maybe -33. So very different from 1 and -1. And that was because of the correlation and this kind of amplification of that happens with that inverse. So now, as we increase alpha, we kind of know what happens on the other extreme. Is our coefficients they shrink to 0. That's not good either. Those are not useful because the true coefficients are 1 and -1. So what's interesting is what happens in between. So if you notice, like for this range of alpha, the least squares, or sorry, the ridge coefficients, in this case, actually get quite close to the truth. And of course, in practice, we don't know the true coefficients, but we can do cross-validation. So here's cross-validation over a very dense grid of alphas. And I'm showing cross-validation mean squared error. And you can see least squares, is doing 26.5. It's actually not terrible, but we can do better. As we start to increase alpha and we get to this regime, you can see that the cross-validation MSE kind of shrunk and it had this plateau, but this point here is actually the very minimizing value. And when we look at that particular alpha over here, we see that that's doing a really good job of recovering the true coefficients. Now, of course, if we keep going, make alpha too big, then bias takes over and dominates us. So this is the best place to be, those alpha there. Okay, so this is an illustration of why ridge regression is helpful, and this is why it's used in practice. Not for feature selection. Okay, any questions? Okay, so in the lab for this unit, you'll see an example of this where there's way more features than there are data. So this matrix here is very, very, very ill-conditioned. You need to do something like this to even make the problem solvable. But in fact, you need to make alpha significantly large, otherwise you're in this terrible regime here. Okay. All right, so that is ridge. Any last questions on ridge? Okay, so let's move on to lasso. So lasso, if you remember, this is RSS, a beta. Actually, sorry, let me spell it out in terms of the norm. So this is y minus x beta norm squared plus alpha times beta norm 1. Okay, so unfortunately, this is not a friendly problem numerically because of this L1 norm. In fact, it's not even differentiable. When you look at this picture over here, you can see there's no derivative at that point. So as a result, we cannot apply the trick we love, which is to set the gradient to 0. That simply doesn't work for this problem. We're going to have to use some other methods. We'll learn about those methods later. But for now, can't use those methods. We just need to compute the solution. So again, we don't know enough to get into the details of how to do this, but there is something special and nice about this cost function. It's that it's convex, meaning essentially it only has one minimum that matters. And that's something we can find using very widely available optimization tools. And so we'll get into the details in Unit 6 of how to do that, but let's just say for now, it's something that can be done. It's pretty straightforward. And it's also implemented in scikit-learn under the lasso method. But more importantly, we want to understand right now how it works. So Let's again take a look at the coefficient path. So here we see something very different. Okay, so if we look on the very far left, is when alpha is very close to zero, once again, this term here doesn't play a role, and we're really just doing least squares. So these coefficients over here on the left are very close to the least squares coefficients. And the same thing happens if we take alpha to an extremely large value, then this term eventually is what we really care about minimizing. This is sort of negligible. And here again, the best thing you can do if you want to minimize this is just set all your coefficients to zero. That's what happens on the right. So what happens in the middle is what's more interesting. And if you look closely, it's very different than what happened with ridge. Here, let's look at the brown curve. So this coefficient, as we increased alpha, got smaller and smaller until it became exactly zero. And then it stayed exactly zero for the remaining alpha. So from this point on, for any alpha greater than this particular coefficient, which is whatever LCP is, that feature is just not part of our prediction anymore. It's taken out. We've done feature selection. That happens at this value of alpha. Now, if I make alpha larger, at some point, the second feature, the pink one, this one also becomes zero, and it's zero from that point on. So you can see as we increase alpha, one by one, our features are dropping out. And so for example, by the time we reach this value of alpha, there's only one feature left that we're using. This is LCA vol. So at this point, we have just simple linear regression, just one coefficient. So this is doing feature selection. That's great. That was the objective of this unit. So any questions on that? Okay. But there's something else happening, which is super important. If you look closely at maybe this range of alpha, for every alpha in that range, there is just one feature being used, LCA vol. But how it's being used is very differently as you go through that range. So here, the beta value you're using is pretty large. But by the time you get to this alpha, the beta value you're using is tiny. And so, obviously the targets are going to, the predictions of the targets are going to change drastically as you change this alpha, even though only that one feature is being used. And if you step out, it's sort of a general trend that as alpha increases, two things happen. Not only do features drop out, but the remaining features shrink towards the origin. So that's what I want to emphasize here. Larger alpha leads to fewer non-zero betas, but also smaller amplitudes for the betas that remain. And that is not something that we want. That is a form of bias. We're forcing the beta to be smaller than we want. Another way to see that is if you would have taken this LCA vol, and if you would have done just least squares regression with that parameter, that feature alone, I don't know exactly the value, but it wouldn't have been like this. It would have been somewhere probably up there. Okay, so lasso is actually not going to give you good performance if it shrinks the features too close to the origin. But anyway, even if we just look at not the values of the betas, but just which subset of betas is non-zero, we learn an interesting thing for this science experiment, you could say. We learned that this LCA vol seems to be the most important predictor of prostate cancer. So that's actually something that is just interesting on its own, and that is something that lasso or any feature selection method that's working well is going to tell us. That's an interesting thing, maybe for the medical community, for science, and so on. Okay, so that's sort of lasso at a high level. Any questions on that? Okay, so let's get into some implementation details, which are going to address this issue of this coefficient shrinkage or coefficient bias. So again, lasso tells us which subset of features are exactly zero, which essentially tells us which ones not to use. But as we just said, the non-zero beta values shrink towards zero. That means they're biased. And so when we use lasso, essentially we want to figure out which coefficients are non-zero. Those are the indices of the non-zero coefficients. Yeah, put that bold. So keep only the indices of the non-zero coefficients. In other words, the set of J such that beta J is not zero. This colon here means such that. Once we know, once we know which coefficients are non-zero, we simply use least squares, which as we learned, let's see, I guess we learned, yeah, we learned that in the end of last unit. We learned that when we do linear regression with least squares, and we keep the coefficients in the true model, we know that there is no bias. So that's the idea. Standard linear regression. Do standard linear regression with the lasso selected features. The set of xj's such that the j is in this set. Okay, so that's how we want to use lasso. Just use it to figure out which coefficients are zero. After that, use only those coefficients in least squares. Now, of course, the remaining question is, how do we choose alpha? Well, we just choose it with cross-validation. Make a grid of alpha, and we figure out the performance for every one of the alphas in between. Now, again, we have to be very careful as to how we measure that performance. And to get into this, I'll show you some naive ways to do it, which don't work as well, and then I'll show you some good ways to do it. Okay, so the first thing we're going to do is we're going to look at a naive way. We're going to tune this biased lasso. This is just the raw lasso where you just use those beta values. So what I have on the right is I have a piece of code which is very similar to the one we saw for model order selection. It has the two nested for loops. The difference is that instead of looking at different hypotheses of model order D, we're now looking at different hypotheses of alpha. And we're looking at 100 different values. But what's important is to use a log spacing on those values. You really want them to span a very wide range. So here we're going from 10 to the power minus 3 up to the 10 to the power 1. That is how we construct our vector of alphas. The other difference is that instead of using least squares as our model, we're using lasso. And here you can see it's again the same library of functions as linear regression, but now it uses lasso. And we're going to tell lasso later which alpha we're using. So basically that's how we set it up. We have the k-fold object, just like we did before. We have our outer loop, which goes over the different folds. And then we have an inner loop, which goes over the different alphas. And so here we're pulling out the alpha value for that iteration of the loop. We are telling lasso that its alpha parameter is A, and then we are fitting it to the training data here. That stores the beta coefficients internally. Then we apply those beta coefficients to our test features to get our test predictions. And then we look at the mean squared of the test minus the true predictions. And essentially in doing this, we're going to fill out this matrix. The matrix we are filling out here is a matrix of all these different sample MSEs where we're looking at all the different folds K and all the different hypotheses of alpha. Once we fill out that entire matrix, we can basically average over the folds K, and then we'll just have a vector of sample of, mean, or you could say sample mean, standard deviation, sample MSEs for our different hypotheses of alpha. And as we know, we can also look at the standard deviation normalized by square root of capital K to get our standard error for different alphas. So now we know both, what's a prediction of the mean squared error, and also how much should we trust that prediction. Yeah. Any questions on what we're doing here with the for loops? Okay, so not surprisingly, there is a shortcut to this in scikit-learn. You can do this whole thing in a couple lines of code. So this is important. This is one of the more important functions you'll be using in labs and final project. It's called grid search CV. So what you do is you tell it the estimator that you want to use. You also tell it the grid of parameters you want to use. So you have to say, okay, first of all, what is the parameter I want to use? It's going to be alpha. This has to be a parameter of this lasso estimator. And then you say, okay, this is the range of alphas, and this is that vector we created earlier, 100 of them, log spaced. Now to do the CV, you have to tell it what kind of CV are we using, and you feed it the k-fold object, the same one that we created here using the k-fold function there. And you have to tell it the score. So just like before, we're using negative mean squared error. So once this is set up, you fit this on your training data. Actually, in this case, it's just all of our data. And as we know, what happens with k-fold cross-validation is it uses a portion of that data for testing, a different portion for training, and it keeps swapping around which portions it uses for testing and training, k different ways. And it returns a vector of numbers. It actually returns a whole bunch of stuff. So here we're saying, tell us the cross-validation results, and in particular, tell us the mean test score, but then also tell us the standard deviation of the test score. And I can use that standard deviation of the test score in order to compute my standard error. And there's sort of a little trick we're using here, is that unfortunately we cannot control whether this is the biased or unbiased standard deviation computed inside this function. And it always uses the biased one. So that means it's dividing by 1 over k. But we know that we wish it was dividing by, it's dividing the variance by 1 over k, which means the standard deviation is being divided by 1 over square root k. On the other hand, we know we want to, for the standard error, divide the unbiased SED by root k, which means we're going to have 1 division by root k and 1 division by root k minus 1. So essentially, we're going to use, here is our division by k minus 1, root k minus 1, and then inside here is the division by root k. So this is sort of a shortcut that you can use. If somebody forces you to use the biased STD version, you make up for it by over here using number of folds minus 1, and it gives you the mathematically identical solution. Okay, so this is just a very quick way of doing what's done over here. Any questions on what we have here? Okay, great. So as we said, what that's going to do is it is going to find the best biased coefficients to use. But we know that those biased coefficients are not what we want to use because they're biased. So instead, what we're going to do is we're going to use do something a little bit better, but it's still not the right thing. So let me explain what we're going to do, or maybe we can see it from the code. So here we're going to set up our lasso. We're going to tell it, let's say we've done our cross-validation tuning as on the previous slide. So now we know the alpha we want to use. And now we go back to our whole training data, no splitting into test train folds. And for that particular alpha, we fit the lasso parameters on that. But as we know, we don't want to get distracted by the bias of those coefficients. So what we do is, okay, down here we can see it. So we look at the absolute values of the lasso coefficients. We make a logical vector by comparing them to 0. This will give us a vector of true and falses. And then we use the numpy where command to figure out which indices make this, this inequality true. So this is going to tell us which of the subset of indices for which we have non-zero coefficients. And we're going to store that in subset. And now, down here, we're going to fit linear regression, but we're not going to use our entire training data matrix. We're going to use all the rows of it, but we're only going to use the columns of it corresponding to the features that Lasso tells us we should use. So this is our feature selected training feature matrix. And now we're using the cross-val score, which we learned about last time, which is just it's not going to do any grid searching, but it's going to say, if you're doing linear regression, and this is your data set, then recursive k-fold says your cross-validation score is, whatever's in that vector. And here we're looking at the mean of the scores. And when we actually we look at the numerical value and we compare that to what we got with least squares where we use all the coefficients, this actually is a better value. So feature selection really did help us. It got us to a better spot in the bias variance trade-off, basically. And when we look at the coefficients here, you can see the intercept is 0. That's not due to lasso, that's because of our standardization. You can see that this coefficient here, it was found to be more harmful than hurtful, so it was set to 0, not used really to train down here. So that's certainly one way to use lasso, but as I said before, it's not optimal. I don't know if anyone can see what's going wrong here. The issue is that the alpha that we're using to do all this stuff here was actually computed on this page, and it was the alpha for which the biased beta coefficients are best. We don't care about how the bias coefficients perform. So that's not what we want to do. Instead, what we want to do, we want to tune alpha to minimize the RSS of the lasso selected least squares coefficients. So let me show you how this works. So now we're going to make an outer loop, or just a loop over the different alpha hypotheses. For each one of those alpha hypotheses A, we tell lasso use that, fit it on our training data, and then we immediately figure out which coefficients lasso is non-zero, and we fit linear regression using that subset. So you can see we are never using the biased lasso betas. We're only figuring out which are non-zero, and then we're basically refitting them with linear regression. And here is the coefficient path as a function of alpha. Actually, not the coefficient path, the cross-validation mean squared error. And you can see it's sort of stepwise. And this is because, if you remember, for all those different values of alpha in this range, it was always using exactly the same subset of non-zero coefficients. And at this value of alpha, all of a sudden, one of them turned off, and it was a different subset. And then here, this one of them turned off, and so on. So that's why it has this stair-step look to it. Anyway, this is the alpha that for which the lasso selected least squares coefficients is lowest. And when we look at that, the cross-validation MSE is even better than the previous page, where we somehow getting sort of distracted by the wrong value of alpha. This is actually a better value of alpha, because this is the one that is really making the least squares final prediction the best. Okay, so this is one approach. Let me very quickly describe the very last approach. So it is using something called a pipeline. And we kind of think of these three operations together. First, do lasso, then extract the non-zero coefficient features, then put them through least squares. So we can kind of think of this whole thing here as one block, one so-called estimator. And we can basically just say, construct this estimator in scikit-learn, and then just give it to grid search CV. So here's the pipeline, so-called pipeline. So it has different stages in it. The first stage is we're going to give it the name lasso, and it does. You can see linear model dot lasso, and then we're also select from model, figures out which of the coefficients are non-zero. The second stage of it takes those remaining coefficients, and it does linear regression. So those are the two things kind of as a unit. And then for grid search CV, we're giving it this. We're sort of treating that as just one estimator, one predictor, and we're saying, do grid search CV on that. So it's going to figure out of this vector of alphas, which is the one that makes that work the best. Okay. And so here, when we plot this, we see that things are a little bit less regular. And this has to do with the way that cross-validation was working. Um, and let me maybe point out something here. It's a little bit unorthodox, is that from the perspective of cross-validation, you could say we're kind of cheating here. We're using our entire training data set to construct, to figure out what is basically the best, not sure you think about it. Using the entire data set to figure out this subset, and then we're doing cross-validation. So whereas over here, we're not ever using the entire training data set. We're always using just certain training folds in K-fold, and then later we're evaluating the test folds in here. So it's similar. The performance is quite close to what we had before. And if we did the one standard error rule, we can get the performance even slightly better. Okay. So that's all I wanted to say today. Apologize for going over. But we have a table of values. I'll go over this for the next lecture. And the last thing is I won't be able to do the lecture on Zoom on Friday. So what I'm going to do is I'm just going to record this and record a lecture for Friday, post it on YouTube, and then send you guys a link. So my apologies for not being able to do the Zoom on Friday. Anyway, sorry again for going over today. And if there's any questions, I'll stick around right now. But if not, have a good one, and I'll see you back in Columbus in person on Monday.
So will you be having office hours tomorrow morning?
Oh, unfortunately, yeah, I won't be able to. I'm not available at that time because I'm in Europe and I have it's like 11 p.m. right now. So yeah, I won't be able to that particular time I won't be able to make. So the TA though will be having a bunch of office hours tomorrow.
Okay, thank you.